Hello. In the last video we were looking at conductors and insulators and explaining why there was a difference between them. I now want to look at the atom silicon, which sits here in the periodic table. You'll see that it's in the n=3 level. It has 2 s electrons and 2 p electrons. And silicon has a structure which looks like this. Here is the valence band, which is full. Here is the conduction band, which is empty. But the gap now is only about 1 electron volt. And at room temperature, where the photons will have an average energy of 1/40th of an electron volt, that still is too big for the electrons to jump across. Of course, a few will, because we know that the molecules in the air won't all be at the same energy. If you look at the energy, you'll find, if you look at that's the number of atoms or the number of molecules versus energy, the average will be 1/40th, but right out here somewhere, you might have a very small number of molecules that do indeed have an energy of 1 electron volt. And so they will enable the electrons to be promoted into the conducting band. But there will be such a small number, 1 part in 10 to the 19 is all you'll get, that for all intents and purposes, silicon in its pure state is an insulator. Now silicon, because it has 4 electrons in its outer level, structures itself rather like this. You have 4 bonds coming from silicon, each of which can bond to another silicon atom. And so you can end up with an array of silicons, each with 4 bonds, and that becomes the silicon crystal. Now, by technology, which I'm not going to describe because I don't really understand it myself, what you can do is you can replace 1 atom of silicon by phosphorus. Phosphorus sits next to silicon in the periodic table. Silicon has 4 electrons in its outer shell, phosphorus has 5. And what you do is you replace 1 atom in a million, 1 silicon atom in a million by phosphorus. And that means the phosphorus will have a spare electron hanging about. What does that mean in terms of this diagram here, where we had the silicon electron valence band and an empty conducting band? Well, this electron, the spare electron of the phosphorus, just happens to sit energetically at a level which is 0.02 electron volts below the conducting band. And now you'll see that a photon of infrared with about 1/40th of an electron volt is perfectly capable of taking that electron and promoting it into the conducting band. So with 1 phosphorus atom per million, you will have those electrons easily put into the conducting band. It won't be anything like as many as you get with copper, where they can pretty much all be promoted. It'll be significantly more than you will get with an insulator, but you will get a nice number of electrons in that conducting band. Now, because phosphorus contains an extra electron, which means that in a sense it has an additional negative charge, this type of arrangement is called N-type. N for negative. You can do exactly the same thing, but instead of replacing silicon by phosphorus, you can replace it by boron. Now, boron has only 3 electrons in its outer shell, so far from having an extra electron, it has as it were, a deficit of an electron. So instead of having an electron, you could almost say it has a hole. And that hole sits just above the conducting band. And therefore you can promote an electron out of the valence band. It sits just above the valence band, and you can promote an electron from the valence band into that hole. leaving holes in the valence band. And holes, which are kind of deficits of electrons, can behave in exactly the same way as electrons in the conducting band. And in those circumstances, it's positive because it's an electron deficit which is equivalent to positive, and that's called p-type. So, an n-type semiconductor is one in which the one silicon atom per million is replaced by phosphorus. That means there are extra electrons. Those electrons sit just below the conducting band and can easily be promoted into the conducting band by room temperature energy from infrared photons. Or you can replace the silicon by boron, in which case you will effectively have a hole, a space where an electron ought to be. Those holes can be regarded as positive particles. The boron hole effectively sits just above the valence band. Electrons can be promoted out of the valence band into that level, leaving holes behind. And those holes can behave in the same way as electrons do in the valence band. And the difference between the two is that the one that has the electrons, the phosphorus, is the n-type, the boron is the p-type. Here's an n-type, and here's a p-type. Actually, I'm going to do it the other way around. Here's a p-type, here's an n-type. P, n. N, surplus of electrons, p, surplus of holes. What happens when you bring them together? Well, there's going to be a little bit of region here where the electrons in the n-type will fill the holes in the p-type, and you get what's called a depletion layer, where you don't have any excess of electrons or any excess of holes. Now let's suppose I apply an electric circuit with a battery such that this is negative and this is positive. What happens? Well, all the electrons in the n-type material will flow towards the positive charge. And all the holes, which of course are positively charged in the p-type, will flow in this direction. And that means that the depletion layer just gets bigger. And the effect is that nothing flows across that depletion layer. No current flows. To all intents and purposes, this is an infinite resistor. But now let's look and see what happens if you take the same P and N material, where once again you will get a depletion layer simply by putting the two together. But this time we're going to apply an electric current, or we're going to apply electric potential such that this side is plus and this side is minus. What happens now? The electrons in the n-type material will simply speed across to the positive side, and they will be fed by further electrons which are coming from the battery. So as those electrons move across, they are replaced by electrons coming from the battery. Similarly, the holes here will flow across to the negative side, and they will be replaced essentially by the kind of the positive charge this side. And now a current is flowing across the gap. And this is quite simply a diode, represented electronically that way. What it means is if you put the bias that way, no current flows. If you put the bias this way, a current flows. And a diode is something that ensures that you can make sure the current only flows in one direction. It's also a means, for example, of converting AC to DC, because when the current flows in the opposite direction, it won't get through, but when it flows in the direction you want it to flow in, it will get through. Now let's look and see what else you can do with this material. Let's take an n-type material, just as we had before, and we'll apply a battery to it like this. N-type material has a surplus of electrons, so no problem. The electrons will flow. But we're not doing very much at the moment, are we? So what we're then going to do is to attach a p-type material. This is N, this is P. As soon as we do that, there will be a small depletion layer just here. But it's only small. It's not really going to have very much effect on the flow of electrons here. But now let's see what happens if we put what's called a reverse bias on that p-type material. When we do that, what's going to happen is that the depletion layer is going to grow. And the more we increase that bias, the more the depletion layer grows. And what that does is it hinders the flow of electrons because the electrons can't go through this bit here. And so the flow of electrons is now moderated by this bias on the p-type material. And that means that as the voltage on this goes up, the flow of electrons goes down, which means that essentially the resistance of this has gone up. And so here you've got a means of restricting the supply of electrons by regulating what the potential is on the p-type conductor here. By making this essentially negative, because of the battery lined up here, you've got exactly the same situation as you had here, where the P was negative, and that simply increased the depletion layer. And finally, we're going to look at bipolar transistors, which are really the heart of semiconductor technology and are the basis of computers and a whole range of electronic gadgets. They basically take N and P-type material and put them together in this form. You get N, P, N. It will work also with PNP, but we'll just use NPN as an example. In other words, you take material that's got a majority of negative carriers, those are those, and then here you've got a majority of, as it were, holes, and holes can be thought of as positively charged because effectively they are electron deficits, so they are positive in an otherwise electron world. Now at first sight, this is madness, because it's never going to work. Let's suppose we make that side negative and that side positive. Well, in those circumstances, the electrons here will want to move towards that positive charge. So they will move across there fine. The only trouble is that when you look at this section here, the electrons here have moved to that positive charge, the holes here have moved towards that negative charge, and this depletion layer has grown greater, and consequently the electrons cannot get across that part. On the other hand, if you turn it the other way around and make that positive and that negative, then the reverse is the case. Electrons have no difficulty getting across that bit, but they can't get across that bit. So it looks as though whichever way you turn, you are going to get nowhere. In fact, this is simply a diode in both directions. It won't allow the current to flow in either direction. So it seems to me pretty pointless. But there is a way that you can use this quite constructively, and it's like this. Let's take our NPN material, and the first thing I'm going to do is to put in a battery like this, so that this end is negative and this end is positive. And you will readily agree that that's going to work because the electrons in the N-type material will move towards the positive charge, so the electrons are quite happy to go that way, and they will of course go right the way around the circuit and come back in again. So this is just a circuit of electrons, and the holes in the positively charged material are quite happy to be attracted towards this negative, and so they will go this way round. So now we've got essentially a flow of electrons going around this way, the electrons being attracted to the positive side of the terminal of the battery, and the holes are going around this way attracted to the negative side of the battery. Occasionally, of course, electrons and holes will meet up and, as it were, just obliterate. But by and large, the electrons and the holes will stay separate as they go round in their alternative ways. Now what happens if I continue the circuit by putting a bigger battery here and making this positively charged? Well, ordinarily, if that were not there, the problem would, of course, as we know, be that the electrons would have no difficulty in getting across here, but they wouldn't be allowed to get across here because the depletion layer would grow much greater. That's what we've seen in the diagram above. But why can't they get across that depletion layer? It is because all the positively charged holes have moved away and all the negatively charged electrons have moved away, just leaving a depletion layer. But when this is here, we've got a flow of holes continuing around here. So as the holes move away, in order to increase the depletion layer, a fresh supply of holes comes in, which means that the depletion layer is not so great. And now the electrons can move not only round in this circuit here, which is what we're showing here, but they can also move in massive numbers across both the junctions. So you get a small flow of electrons this way and a massive flow of electrons this way. So for a small flow of electrons, i.e. a small current this way, you get a massive flow that way. And that is the basis of an amplifier. For a small current coming in here, you can get a very large current coming around here. And that's the basis of many of the amplifier technologies that are around today. And that all comes, let me remind you, from the quantum mechanics that we started this with.